Hi, good afternoon. I'm Julian. So it's a great honor for me to chair this session. So I'm from University of Wollongong Intelligent Polymer Research Institute. So without further ado, I would like to welcome Professor Gordon Wallace to have the opening remarks. Thank you.
Thanks, Julian, and just echo Sam's comments, and thanks everyone for joining us. A special thank you to the members of our International Advisory Board who are with us, and a big thank you to the International Advisory Board for all of their guidance during the lifetime of ACES. So we're in for a bit of a treat today, just having a look at some of the high impact things that have come out of ACES. As you know, ARC funding for our entity wound up in December 2021, but we are still operating under the ACES umbrella until the end of this year. And our real focus during this year is to provide as much support as possible to continue to build new initiatives and new collaborations built on the ACES knowledge platform, and also to consolidate the many initiatives that we have across Australia and indeed across the world. And so Sam and Tracy and I are still here to assist in anything in that regard. And particularly in terms of the communications, we want to keep the website alive and make sure that the world knows about these collaborative opportunities. And part of that, of course, will be the recordings from today that Sam will get up onto the website in terms of the technologies that have been developed and are coming out of ACES. I think you'd all agree that there's many opportunities for ACES researchers, particularly in Australia at the moment. There are a number of new initiatives in terms of translational funding, and of course we're very well positioned in order to tap into those opportunities. And I know there's many things on the boil and many exciting developments already early this year, including our involvement of some of our researchers in the Mend the Gap spinal cord regeneration program being run out of Canada. Sam's really keen to continue to collect all of that type of information as well, and to keep our website alive over the next 12 months. There are a number of working groups that have been established to develop new program areas involving ACES researchers. They include the Green Electrolyzer Technology Initiative, the Materials and Fabrication Methods for Space Initiative, Electrofluidics and Diagnostics, and finally Electroceuticals. And if anybody has any interest in those groups, maybe just contact Tracy initially and she'll put you in contact with the leaders of those programs as we develop them through the remainder of this year. So we've got a great program today, which will really highlight many of our knowledge initiatives, if you like, our groundbreaking research and what that has meant, not just from a fundamental point of view, but a translational point of view, and how it's built opportunities in the translational environment. I think everyone would agree, and of course we're writing our final annual report at the moment, but along with all of the great knowledge and the translational facilities that we've been able to create in the lifetime of ACES, of course, we also have created an amazing generation of researchers, and I think we can all be proud of that. Researchers that have been trained in an environment that is interdisciplinary, that is outward-looking, that does emphasize the need for communication skills that go across different technical disciplines, but also across different non-technical disciplines if we're going to be successful. We have, of course, many collaborators around the country and around the world, and a big thank you to them for their part in making ACES successful, and a big thank you to them going forward for how we can work with them in building new collaborative initiatives. So again, thanks for joining us today. We will make the most of these recordings in terms of the impact that ACES has been able to create. And again, a special thank you to our International Advisory Board members who could join us today, and a number of guests that I can see on the screen as well. Thank you for coming along and having a listen to what ACES researchers have been able to achieve. And that's it, Gillian. I'm done. Thank you.
Thank you very much. So it's time to welcome our first speaker, Professor Rob Kapsa. it's a little update. Professor Mark Cook, he sent his apology. So Rob will introduce you some exciting discovery in synthetic biosystems sim. Thank you, Rob.
Thank you for the intro, Gillian, and thank you, Gordon, for and Mark, I guess, for giving me the opportunity to give this wind up. And the first thing that I guess is apparent to me, at least, is the fact that we started off with an earlier ACES, and that a lot of the work in the synthetic biosystems came from the bionics of the previous ACES. And we learned a lot of things there about electromaterials, us biologists. And we realized that essentially the whole thing about, I hope that's not showing to you. But anyway, so it's all about excitable cells, and that is muscle and nerve. And that's cells that are able to be stimulated by electrical stimulation. And that's where the precepts for the synthetic biosystem for the second ACES came from. So we realized, or realizing this, we had a primary interface where we were working on mainly CNS issues. And then we had some background projects. There were other areas that we were considering, and we kept them in mind as we went, but primarily we were looking at advanced neuroengineering scaffolds for muscle and nerve and neurological disorders and perhaps neurotransmission. So the system that we were adopting was a circular system where we were introducing nanodimension and making microdimensions out of that. And there was a little bit of an eddy that was going on that way, and then the microdimension to the macrodimension that was working within the Electromaterials system. And that was then informed by the biological cell systems that we had that we could then feed some of the information back into redesign these processes, and then result in making either models or scaffolds for re-engineering CNS in the first instance, and then muscle in the second instance. So off we went. We set out in the first 3 years predominantly working on the materials. So the first 3 years was looking at establishing what sort of materials we needed to do what we wanted to do. And we ended up revising these milestones into, or refining them actually, more than revising, on the basis of what we did in the first 3 years into the next 4 years. And we had a couple of grants that were orientated in the nerve area. So there was a CNS one here with Professor Huang at UOW, and then there was a grant that I had as well that was looking at nerve matrix. And this then fed into these programs that came out of, this is directly out of the initial project plan. And then we had a few people that we needed to find, but essentially we had people working already in 2014 on pretty chunky aspects of this program, and we had some good money that was coming in to assist. So what were we going to do? We decided, well, we need a black box, okay? So we thought, this was the first thought that we had. So I went off to Steve Byrne and I told him that we needed a black box. And surprisingly, we came up with a black box, and that was going to be the black box that we were going to look at configurations of hydrogels with cells and all sorts of goodies in there. So neurons, laminin, fibronectin, alginate, whatever. And we were then going to go through another iterative process to try and make something out of this that could basically be used in forming the neural structures that we were looking for. And then we were going to feed back. We had various points at which we could sort of adjust this process, but this is what Steve and I came out with. And to my surprise, I don't know why I was laughing, but I couldn't show Tony's face here, because this is when we said we were going to spend millions of dollars doing this. And that was the reaction from Gordon and Mark there. So I don't know why I'm laughing. But anyway, we decided to redress this, and we came up with the second prototype, which was a pseudo-fluidic sort of thing, where there was a little vessel for cells that was going to be gravity fed through there, and we were going to collect the materials out the back of it. And we actually got to printing this and doing some tests on it, but it wasn't very good. So we fitted that into our program, and what it actually allowed us to do was to really hone in on what we actually really wanted to do. So we wanted to use growth factors, drugs, nutrients, putting it into this system, and then we were going to look through what came out of the system in terms of how the cells inside there were going to actually process the environment and whatever went in there. And we came up with, it made us really hone in on exactly what we wanted to do. So we knew we needed materials, so we had a suite of materials that we wanted to do. And we had this electrofluidics nutrients, and we wanted to control all of these wastes and bioagents and metabolites. And there was a little bit of a thought bubble that was always following us around, that we wanted to somehow incorporate the energy platform to see how we could actually make better systems. But what we really found is that we really had a deficiency in terms of what we wanted to put together, in terms of what we could and couldn't do. Okay, so when in doubt, bring in the experts. And so we spoke with Brett. I always do that. But we spoke with Brett and his team down in Tassie, and we came up with a series of tests that they could already do. So we focused on what they could do, and we wanted to integrate that into the system. And this is what we came up with, this Nemo system, which is got a fluidics, a microfluidics structure. And there's pumps here for whatever you want to put in. There's drug delivery systems here. There's gives you some kind of information in terms of what's flowing through there. And then there was a very, very dichotomized fluidic structure that then fed through a cell culture chamber that was 3 millimeters in height, which mimicked the brain cortex. And here are some of the pictures of the prototypes that were made. It's primarily made by Neil McDonald and a couple other people there. But we did unfortunately have a personnel change. But in the meantime, we developed a very, very strong activity around this system that involved Swinburne looking at the delivery aspects. So there was glutamate, neurotransmitters that were going to be in there. There was an anti-epileptic drug that was going to go there, and that would give us an ability to stimulate neurons within this structure in a way that could mimic start to try and create a model that involved putting a certain amount of this inhibitor to activity to try and emulate epilepsy, fine-tune the epileptiform activity, and then see how you could treat that with the anti-epileptic drugs. And of course, then there was the sensing part of it was to be done by UTAS, and then there was this big conglomerate of people here that were involved in the electrophysiology of recording the brain signals there, so that we could establish what was actually going on in there at the electro-excited. We left that one behind, and along comes Paull and Brett again. And the final model was, it was, I guess, putting a square hole in a round peg, and that was to accommodate the the electrophysiological setup, so that you could stick this over the top of a MEA chip, and you could then have a much higher 3D kind of 3D sort of presentation of the fluidics through the system. So this resulted in a company that that Brett and Paull are running, and it's one of the legacies, I think, of the well, it's the collaboration between Fluidics and SBS. So on the biological side, there are a number of projects that kind of, this is a point at 2020, but we had about 6 projects going that range from electrical stimulation of the neural tissues and organoids. We started working on organoids in both in Wollongong as well as in Melbourne. And so there was a schizophrenia focus up in Wollongong and an epilepsy focus in Melbourne. And in addition, Simon and his crew were running some delivery paradigms that were to go into that original concept. So we also got some results in terms of the background things. So there was a project here on osteoinduction of human stem cells by fabrication of corneal tissue, and back in the 90s that we managed to make some incredible muscle. So this is normal muscle here. This is the muscle that we made, and there was neuromuscular junctions that we noticed that we could make out of that. Some excellent work done by Catherine Yan there. And that then led to some other projects here where we were modelling epilepsy here. So we have a epileptiform set of organoids and another set of organoids that are non-epileptiform by the difference of a single nucleotide in their genome. So these are real epilepsy from, anyway, getting the organoids there. And we had Eva and Jeremy were working up there on wireless stimulation for activation of neural organoids up and getting more rapid modelling. And then there was some cell encapsulation studies and the delivery studies being done by Simon and Lilith down here in Melbourne. And then there was some muscle modelling systems that we were using as well. So that was here. You can see these muscle firing that's occurring in all sorts of different ways. So the legacy, I guess, you know, like we were involved in the legacy activities that David was running, and it's a good thinking process. And one of the things along the way that has really come out is, as Gordon was saying, there's a generation of people that are out there that have been profoundly affected by what we've done. And so were helped to be formed, and one is AB3D at ACMD. So this is a printing facility, bioinks engagement, clinical interface, and it's a precursor to a much larger institute that's being formed called the Aikenhead Centre for Medical Discovery that is going up on the corner of, at St Vincent's, and the biofab came out of our activities in ACES as a way of showing what the benefit of having a facility with scientists all over the place, and you know what the power of that is. And of course there was the famous biopen that led to Accelera, and I don't know what else there has been. And then there's the neuromuscular junction interface, which has led to some very interesting aspects within the field of robotics that we developed with Peter Chung and Catherine. And then there's this Nemo construct that kind of lives on in spirit, and that led to new hydrogels, new 3D neural constructs, and neuromodels with different release type of paradigms mainly for epilepsy and schizophrenia, but these will be carried forward in other directions at a later point. And then there was our involvement in policy and education with the Masters in Biofabrication at by the EPPE platform. So I guess that's really all I've got to say. There's a list of where these things, there's a lot of people that were involved in all of this at ACES, and there's a few of them that are maybe a little bit more well, not everybody's involved to the same degree, but there's a few of them that were real contributors here. And I love this picture of Simon here. Every time I see him these days as the professor, I like to think of the tie that he's wearing here. It's always a good look. But on a more serious note, you know, like the thing with ACES and SBS and everything that we've achieved has been because of the people. And that's what we carry forward into these institutions who will carry on the work beyond what we've done in 2 awesome programs. So with that, I'd like to wave goodbye to you all here. That's the robotics thing. This is powered by muscle cells grown on a multi-electrode array. And that is one of the principal flagships that we're carrying from our point of view, Anita and mine, into RMIT and then into this ACND. So with that, I'd like to finally just acknowledge Tony Campbell for having done an awesome job in keeping us all together and herding us cats and making things work so well. So that's it from me. Thanks very much, everyone.
Thank you, Rob, for giving such an overview. It covers a variety of aspects ranging from material, printing, fabrication, microfluidic, and 3D modeling. So now we open for questions. So first I got a question from Gordon. Thank you for overview, Rob. So looking forward, what will the brain on the bench look like in 3 years? And is there a need to bring in other skills? Thank you.
Well, I thought you would never ask that. Well, I think the brain on a bench has got some really good potential. So, you know, what you're seeing here is we've got models of epilepsy. We've been able to make these 3D gels where what happens when you look at the difference between these firing patterns here, when you put things in 3D, it makes it work like a brain. So there's a brain pattern that came out of a human brain. This is all rat. But nevertheless, if you do things in 2D and then you change them to 3D, you get more of an activity that's reflective of what actually happens in proper brain. So that then means you can make structures like this. So what we have here is where we have this person who has a mutation that causes an epilepsy syndrome, and that's shown by these you know, haphazard firing of the brain, right, in this organoid. And what our collaborators did is they removed the mutation and they generated the same kind of organoid, but you can see that you've removed the epileptic activity there, right? So what you can do is you can actually take this and you can put it into a 3D thing like this, and you can then fine tune what chemicals you put in. So remember, the Nemo construct had the glutamate, the GABA, and the anti-epileptic drug, and then that you actually present to the 3D structure, and you will get propensity, like some brains might be more prone to generating an epileptiform activity. You can put them under pressure. So neurotrauma is associated with a certain amount of pressure on the brain, and then you can maybe do things. You can make models for sports people to see if they're particularly prone to concussion. So we have there's this guy called Pekowski who's a cricketer, and he's now just had his 11th concussion, and he's probably never, he was prone to getting concussion. If he puts his head in front of the way of a cricket ball, then maybe he would, have a cricketing career. So that's where I see the brain on the bench going.
Thank you.
So is there a need to bring in other skills?
Oh, other skills. Oh, where do I start? So you know, you look at something like this, where there's a neural version of this where you have sensory neurons. So this is a motor interface that moves this hand, and that's what I was showing you before. And the other version of this involves neural tissues, and you need to make a 3D pics. You need the people in the software to control things. I had a slide that I've been showing around that actually says that, and there's millions of you know, there's millions of different types of people with different types of skills that you need. So, you know, we were able to put this into a rat using this model. So you need neurosurgeons to make this arteriovenous fistula, creates a biological capillary network in there that you can implant in a rat. You can put a nerve in there, and you have motor nerves going to this, and you have you know, the sensory nerves going to the other gel that we make, and that will then be the basis of a hand that feels. Now, how many other people do you need? You need surgeons, you need orthopedics, neurosurgeons, you need all sorts of people to make these things work. Okay,
so any more questions? If not, we'll move on to our second speaker, Professor Jenny Pringle from Deakin University. Her talk is Innovations in Training the Next Generation of Researcher. Professor Jenny Pringle, please.
The chair, hopefully you'll interrupt me if you can't see my slides. I've changed slides just to show you the aim, which is what we really set out to do, was to design and implement, I guess, quite a new aspect of research and training and career development. So really the idea is to train PhD students and early career researchers and so forth to make sure that they have the skills needed, not just for the jobs there are now, but the jobs really for the future. And I think even Rob's presentation before shows the kind of, you know, diverse expertise that are needed, not just now, but if you imagine where all of that technology is going. And I think one of the key points here is that for a centre of excellence, you know, there's such a wide range of expertise in our centre, and, you know, it's multidisciplinary. There's people at all the different career levels. And so students within a centre should benefit from that. And I think that's kind of the approach that we've taken in a lot of this training, to make sure that they really feel the benefit of everything that's being done in the centre. So we focus on three key things: communication. Gordon's already touched on how important that is, commercialization, and research management. And so ACES overall trained at least 50 postdocs, more than 75 PhD students. I'm sure it's even more than that if you count all the affiliate students. So it's, you know, quite a large undertaking. In terms of research management and leadership, so again, beyond the slightly traditional approach, there's been a few aspects, and some of these are just the way that the centre was sort of set up, so not necessarily, you know, formalized, but for example, the idea of supervision and mentoring across the different career levels. So for example, a new PhD student is always given a buddy. You know, the older PhD students mentored by the early career researchers. There was the opportunity for the ECRs and the junior CIs to serve on executive committees to see how those work. Even the fortnightly video meetings and theme meetings and the face-to-face, you know, full centre meetings, these are amazing opportunities to learn from the different disciplines, insights into project management, great practice at presentation skills, and the quality of the presentations in those meetings was often really, you know, exceptional. And it's also just a way of exposing the students and the researchers to seeing everything from the new materials and the modelling right the way through to the actual research translation, and hearing from sort of about the end user interactions and I think for students who've only ever been part of ACES, perhaps don't opportunity is to see all of that. So, you know, in summary, there's been training on communications, because that's so important in being able to engage across different disciplines, and also to explain, you know, the research and what we do and why it's important to the wider community. And I'll touch on outreach in a minute. Entrepreneurship and innovation has always been very important, and I'll mention the short courses, but also, even as I've said, just experience of that kind of research translation, hearing from some of the spin outs that have come from ACES, for example. And of course, you'll be aware that there's a really strong ethics and public engagement theme throughout the centre, so that make sure that everybody is aware of the ethics and the policy issues that can arise from the research. Professional development, of course, and that spans everything from, for example, paper writing. That was done initially as a 5-day course with people working on their own particular papers with feedback from the tutors, also right the way through to short webinars. So sometimes a range of different ways of delivering something can meet, you know, the needs of a more diverse audience. Even simple things like project planning and management, student supervisor relationships. So some of these were workshops, others were given as presentations, for example, at the full centre meeting. And then as we progressed, it is important for people staying in academia, and then sort of an increasing emphasis on the career development in terms of how do you write a CV and a cover letter, and also what's next. So we found panel sessions to be, you know, really valuable in terms of, you know, they say you can't be what you can't see. So hearing from people who have moved on and moved into lots of different careers, how did they do that? You know, how did they even get up the nerve to apply for jobs that they weren't necessarily qualified for? You know, that kind of feedback in terms of careers was also, I think, really useful. Of course, we've run lots of different technical skills workshops, and I'm not going to read through them all, but I think one of the key points was that these were open to everyone. So, you know, your PhD project might have been on solar fuels, for example, but within that, you know, it's really important to learn about the electrolytes or the different analysis techniques, or you might just have an interest in how do you make 3D printing and fluidics. So again, it's about tapping into the expertise in the centre. And then there was more sort of holistic training programs as well. And for example, there was quite early on, there was the Science of Collaboration workshop. And we ran a 2-day intensive on science graphics, because of course, increasingly graphics is really key, and it can make a difference between, you know, getting that high impact paper or that journal cover or not. I think key has also been integrating the sort of end user as well into the ACES and what we do. There was a fabrication fellow program, for example, and then also more recently the idea of technology showcases, where the researchers and sometimes the PhD students will develop, you know, these showcases to show people, for example, just as a stand on the full centre meeting, or portable exhibits to go and talk to other researchers and other end users. And then, of course, ethics workshops, as I mentioned. For example, one of the earlier ones was the Therapeutic Goods Administration. There was a workshop on the bioethics of, you know, to do with the biofabrication. But and again, I think throughout this slide really emphasizes again the idea of bringing in the experts across the different fields and to really strengthen some of this analysis. So that you end up, essentially, if you imagine you end up with a researcher that is skilled across all of these different things, right, from the technical skills to understanding the needs of the end user and how to do that in translation, but also to understand the ethical implications of that, and how likely is it to be up, you know, that for that technology to be taken up, and what are the implications of that. We've run quite a few different communications workshops. Here's an early example that Questacon ran back in 2014, talking about how do you communicate your PhD research to school children, and this idea of working with teachers and educators and even teachers in training, I think, is a really great way of getting in at the ground floor and starting to influence that conversations with the next generation of scientists. And I'll mention that those activities again at Deakin in a minute. And we've also run workshops run by Science in Public, and what was really special about those was we had real live practicing journalists. So this panel of 4 journalists that you can see in the photos, for example, from the Herald Sun, from the Age, from the Conversation, explaining what makes a science story and how do you pitch your science and your research. So that people will understand it and be really engaged in it. And there was also training on how you make a video about your research as well. And some of those went online. And there was one centre meeting, we did a presentation training from a positive psychology coach. So a slightly different approach, but again, so important. How do you get the confidence to stand up and make these presentations, which doesn't get any easier, but it's something that we all have to do. The Innovation and Entrepreneurship Certificate, of course, has been really important and I think very successful. So 110 ACES students have come through that course so far. Really, it's about understanding a bit more about the business aspect of it and in terms of the translation. So the idea of how you can take a research project and place it into a business context and how you might commercialize that and all the aspects behind that. So again, some expert speakers. This was run by the Sydney Business School as well, especially as an intensive to start with, and then of course moved on online later. And you'll have seen the pitches at the full centre meetings from the different groups that have come through that course, and some of those video pitches have then since been entered into competitions. And for some people, this is their first look at that business aspect, and it's really inspired them to go on and really sort of seize those opportunities in more detail. So again, I think quite a unique opportunity there. We run quite a few summer scholarship programs, and so for some people this is their first taste of research, and sometimes it does inspire them to stay on to do a PhD, which I think is a great outcome. One of my favorites, I think, was the science and suitcase idea, getting them to develop these portable demonstrations of their research, so that again you can take these out to the teachers or to the general public and explain what it is that you're doing. And then there's been other more lab-based projects, for example. A range of other outreach activities. So we've been quite revolutionising maths and science teacher education programme. So again, this is coming back to the idea of teaching the teachers. So these are pre-service teachers, they're going to go out and be science teachers, and getting them involved and sometimes just explaining to people, what does research even mean? If you say, well, I research batteries, people say, well, I can buy batteries. Why do you need to research them? So how do you explain the challenge? What are you trying to fix? How do you go about designing those experiments, for example, and what to do next? And taking a real step back and getting people to explain that, it's great training. And I think it gives everybody a real boost. And also, we did actual practical lab classes. These are some quite early photos, and there's at least one person in this photo who now works in a school full time and is really enjoying it. So, these students are often taught about things like spectroscopy, fault of the school, but it gives them a real boost to come and actually do that lab class, get given some unknowns and use the spectrometers to understand what they are. And it's really great and unusual training for the students. Of course, master's courses has been a really important outcome as well. And the Master of Biofabrication, I think, is another one that's really evolved and sort of meeting changing needs. So it started off, I think, really with the MOOC, the Massive Online Open Learning Course. And I think more than 27,500 people registered for that course in the first couple of years. Now it's available as, it's morphed into this online grad cert. And then for those who want to do the whole hog and, get the printers and do the practical applications, then there's also the MPhil at Wollongong as well. And so again, it's another, I think, demonstration of how you can tailor this research training to meet different audiences. So for example, these people might be professionals who are going to have to start learning about these things as part of their career, or they might be people in academia who are just interested. So I think the more that you can deliver these things in slightly different ways, the more successful it will be as a research training activity. The MPhil Electromaterials was the core that we said that we would set up to do, which was established as the first joint degree between Deakin and Wollongong, and in fact the first joint degree between Deakin and any university in Australia, and the first Master of Philosophy as well. And sort of there have been others that have followed in its footsteps. And this was a really great cross-nodal activity where there was lectures from both places. So great lecturing practice for the CIs and ECRs involved. And for those of us who work in research institutes, we don't often get the chance to do that lecturing, which is a super important experience. And then also cross-nodal supervision of the research thesis as well. And ACES through Deakin is also part of a European master's course in materials and energy storage and conversion. So we host students for their internship projects, and we have a scholarship for one of them, hopefully due any day now. And it's just another very useful international collaboration, in this case with energy storage groups in Europe. And then 2020, so, it all moved online. And I think it's fair to say that we were, one of the first groups that started to, produce a lot of, good quality webinars. So everything from training. So this is Doug's writing a great paper webinar, which always gets a good audience. Panel discussions, again, this is a great forum for bringing together people who wouldn't. These discussions have proved, really insightful. Or to your more traditional sort of research presentations. And these are all still available. It's a great resource for going back and having a look at any of these. They're all available on the ACES YouTube channel. So that's it, my thank you slide. Thank you to everyone that's been involved in this. I haven't been able to mention everything, but big thanks to the ACES Research Training Group. And I'll take some questions. Thank you.
Thank you, Professor Jenny Pringle, for showcase those wonderful education program for training next generation of researcher. Now we're open for questions. So we got one from Professor Gordon Wallace. Thank you, Jenny. What bits of the ACES training program can we capture for others to use in the future? Perhaps we can get funding for some of these. Thank you.
Yeah. Oh gosh, it's difficult, isn't it, to sort of pin down one bit. I mean, I think the things that came through for me when I was sort of trying to summarize all this was as I said, the ability to capture all of the different expertise, but I'm also passion and excitement, even at the school level. I think just as a way of demonstrating, this is what it means to be a scientist or a researcher, or this is why we do what we do, and that enthusiasm and passion. I think that's super important. And I think, that's one of the things that I would like to work out how we really continue that. I don't know if that answers your question, but that was my feeling from putting this together. It was one of the most important things that came out. Yeah,
thanks, Jenny. I think there's some amazing stuff there. It'd be just great to do a bit of an audit as to where we've seen some, opportunities that are really worth trying to get some funding to sustain that activity, given the runs that are on the board already.
We got one question from, sorry, I'm not sure.
From Ashar, yeah, I can see. So are there any creative sort of lab management courses involving multidisciplinary research in practical situations? Look, not that I know of. Yeah, that's all I can say. I mean, that would be nice, but not that I know of.
Okay, thank you. Any more questions? So now I would like to introduce our third speaker, Professor Gursel Alici from University Wollongong. So he's going to talk about software robotics for prosthetic devices. What difference we have made. Thank you.
Thank you, Julian. It's my great pleasure to talk about what we have achieved, and equally importantly, what differences ACES made in our career and in our students' career. So before I say anything technical, I would like to thank every member of ACES, Gordon, Maria, all the leadership team, Tony, advisory committee members who are online, some of them now. It was a truly successful and wonderful experience, not only for me, for my colleagues and for my students. So we enjoyed it. We made significant differences in our career, in our life, and we feel much, much better. So I should appreciate that one before I say anything. So let's start what we have done. As you know, Soft Robotics team is one of the applied teams in ACES, and we bring the engineering applied side of expertise to ACES. The aim is to explore and demonstrate the potential of the electromaterials prone to additive manufacturing, and use these materials as printable actuators, sensors, mechanisms, new soft robotic systems, and especially their demonstration in prosthetic devices, in particular prosthetic hand with natural control. So if we can bring prosthetic devices one step closer towards their natural counterparts, it would have been success. And we did. As you can see some samples on my desk, I will be showing you proudly that we have achieved lots of great things, not only with our team, but all other teams in ACES. And you can see our team members. You know, it's not a big team member compared to maybe others, but I think we believe together with the big ACES family, we made some significant contributions and achievements. What are these ones? Let me briefly explain. I'm not going to tell everything in detail. The details are in the papers, in the publications, in the thesis. So one of the notable ones is to establish a soft actuation concept in line with the goals of ACES, as well as milestones of our team, Soft Robotics team. So this idea was inspired from fern trees. While I was doing gardening one weekend, I got this inspiration and then talked to one of our PhD students, Charbel Talk. I will show his very wonderful picture soon. And the idea was to use vacuum to develop a bending. Maybe I'll show the next video that will save me lots of words. I mean, I have that actuator with me. I don't know whether you can see or not. It's all real time. The idea is to apply a vacuum like the fern trees do. Fern trees do opposite. So they got curl and then they open up when they grow. So the idea is to have this concept, if I can go backwards, and we characterize, of course, in every decision we made, we had to inform our decisions through some scientific analysis, like engineering analysis, modeling, optimization, numerical solutions that they are not doing it randomly. So one of the ideas was to develop a robot called Gongeru. It's a creative name belonging to us, Wollongong and Kangaroo. So it was one of those jumping ones, and this actuator are the leg of our Gongeru, jumping one. And it was a quite successful one using low-cost printing, some off-shelf thermoplastic polyurethane with one step, no further processing. And also we demonstrated the actuation concept in a walking robot as well. So this was a significant one published in this top robotics journal called Soft Robotics. And these are some extra characterization, and it's quite high. It can carry 26 times more than its weight, significant force output, etc. Maybe I'm not going to here. And we did lots of optimization with some samples, again, on my desk. And we made sure that what we are doing is meaningful and we can explain what's happening from fundamentals. And this is the video I just showed you. And what happened in 2018, we participated in a competition in the biggest, most prestigious robotics and automation conference in the world. It was held in Brisbane. We thought as locals, we can go there, and we participated in soft component technologies with these actuators, and we came first as SOA. SOA is the acronym we use for our actuators, as written there. Sorry, here. I think I pressed the wrong button. Let me quickly jump to where we were. That's SOA, and this is, then we made it as linear version called L-SOA, making linear one again. I got a sample in my hands, published in this prestigious journals again, and then we use this L-SOA to build a gripper. Again, the gripper is here. It's retired, but it's still working. And sorry for that blue bucket. That was the most expensive one as per our budget. And this is the robotic arm in our lab here on the main campus. And we did a wonderful job and publishing this journal. But more importantly, in the same conference, we participated in another challenge, gripping challenge. And our hand, multi-purpose hand, came first, handling 15, 16 odd objects in a shortest possible time without dropping them. So that was another significant achievement we had. I didn't see Charbel's picture, so I don't want to be on. Yes, he's here. Charbel is currently an assistant professor at University of Wollongong in Dubai in mechanical engineering. So that's another outcome we should be proud of. And another piece of work we did on soft actuators was done by the PhD student, Dr. Hu, I should say. She came with her own scholarship from China. Now she works at Shenzhen Institute of Technology in China. We came with a very simple idea. Rather than having straight chambers like this one, we can 3D print angled ones, like 45, we optimize 40, 45 degrees in any way. And then even we can have combined ones. So we use this simple idea to develop a gripper or other systems in line with our goals to develop application-specific robotic devices like a gripper. So this simple idea, again, based on 3D printing one step. So we call it angled pneumatic networks. This is the acronym we coined. It can generate bending and twisting simultaneously because it's not linear. If it's linear like this, only bends. And what we did, we characterized these ones and found that for the same pressure, same volume, this angled one generates significantly higher force. In a way, we optimized and from 1.19 Newton for the straight ones to 2.1 Newton. So that's an amazing mechanical efficiency. Material is the same. It's the weight of the actuator is the same, just using some clever ideas, making the actuator prone to bending and twisting at the same time. And this is also something to be noted. Next, we developed also, now we have the expertise to develop human-machine interface to pick up signals from human body. For example, here we considered 4 modes, like touch. We can push this one to generate a signal. This is squeeze one, the square one, sorry, I think I can read it here, and the bending ones and the twist ones. So we can program these ones to control any device where you need to control it. So we called it soft pneumatic chambers. That's the fundamental idea. These are the soft ones, and we use a solid state low-cost pressure sensor, we purchase them very low cost, and we measure the pressure change in these chambers and then use this change to make decisions about what the human wants to do with the machine. So this was a quite successful piece of work as part of Charbel's PhD thesis, and we characterized successfully applied to many places, many applications. One application together with Hao Zhao, who has been in the last 5 years as the research fellow in the soft robotics team, to use these soft chambers in the fingers of a prosthetic hand. I got that sample in my hand. We can see whether when the fingers bend, we can estimate where the finger is, where the position of the finger is. Nobody did this before. So we use this chamber as part of the finger to estimate where the finger is and then control it. Later, I will show you our recent piece of work in another strong journal that we can even optimize the grasping, which nobody did before. So these are some impacts based on our fundamental work on developing some soft sensitive chambers. Another piece of work in sensors done by Dr. Vitor Senjades. Unfortunately, Vitor returned to home country of Portugal 6 months ago, and he led this work on piezo-resistive and capacitive foam sensors, who are very sensitive, like the piezo-resistive one can measure or estimate the mass of rice grain, I think it was around 34 Pascal. And this can be again used in grippers. I have one gripper here to handle soft objects like mango or some agricultural produce, which is sensitive to touch. So this can be used to empower robotic system, which we did. It can be used in human-machine interfaces. Even Charbel had a piano playing some Christmas songs using these these sensors under his finger to generate some various notes and music pieces. So it's again, we are very happy and excited that we can sense and use that signal, control any device, a finger or a gripper or a robotic system. So these are some work. And then we continued with this work, if I can go backwards, sorry. Developed these wearable technologies, and last year we submitted an ARC discovery grant. We got good comments, but you know how it is, and we didn't get it. And the idea is to get signals around the body for health monitoring. And it was also a wonderful piece of work published here. Very sensitive microcellular structures in those sensors made them highly sensitive and durable. And we made some characterization that their touch sensing capability is close to human fingertip. That was also a wonderful thing. Of course, we developed some strain sensors. It's a bit old work, but doesn't matter. This is also some work we developed using some graphene ink to control some of the prosthetic fingers we printed before and do this one. So I got that one again, very durable. This was also very important to estimate how much bending is happening at the joints and then drive the fingers. So there are some various tests here that, although they are being subjected to some scratch, mechanical hardship, I should say, they do a great job. I mean, I don't want to go further into these ones. They are there. The biggest, one of the biggest contributions we made was in bilateral control of the prosthetic hand, which we did. You can see in the picture. And in 2020, I think we had a showcase, and this video is here. I don't want to go into the hands features. What we did, you can see on my desk some of the hands we developed, and also one of the prosthetic hand companies in New Zealand, Tasca Prosthetics, donated us a prosthetic hand worth of $30,000, which we used to test our control algorithms, to use various electrodes to determine the human's gestures using some electrodes placed on the lower arm, and then use machine learning to identify various gestures and control this hand and ACES hand. So we have a number of ACES hands now. It's version 3 in a publication, and we compare with a commercial one. Making hand is not a problem. Problem is controlling it. Problem is having bilateral control, sending sensory feedback. So in that regard, what we did, we collaborated with our other colleagues, especially colleagues in our EPPE, Ethics, Policy and Public Engagement team, and Mary Walker and Goddard. We did some survey, determined what prosthetic hand users want, and also we collaborated with people at Prince of Wales Hospital in Sydney, Department of Rehabilitation Medicine. And of course, these are the students and researchers who contributed to the user-centered design of the prosthetic hand, its forward control, as well as the feedback control. Benjamin completed his PhD thesis on that topic, and now he works for Facebook in Seattle, and so he's our representative there, working on touch sensing on some Facebook products. So currently, lastly, I'm very conscious of time, make sure that I'm on track. The last piece of work on top of what we did since 2020, so you can go and see this link. And after that, Hao and Charbel are working on ACES version 3, how we can use chambers and also sensors at the tip of the finger. So I got one sample here, like our flash. It can measure the contact force as well as we can measure the joint force, the finger forces, finger positions. and then control where the finger is. So this work is going well. It may look ugly, but this is a very sophisticated experimental setup, fully designed, built, tested by ACES, resources. And in this work, what we are trying to do, colleagues, here there are lots of things. The current prosthetic hands do gestures, but they have to go to their neutral positions. They do this gesture, for example, they have to go to fully open and then do this one if you want. What we are proposing in this work is, if the hand is like this, can we do this one without going back to the open one? So the numbers here shows we halve the transition time. We shortened it and we approach one step closer to natural hands rather than artificially going there. So we use built-in sensors and also did some work. Another piece of work we did was to know where the other fingers are. We can send the fingers, not necessarily still running the fingers until it touches and overloads the actuators. So as soon as the finger touches, we know there is something, then it can stop, and then it can apply a minimum amount of force. So there are some videos. This is the publication I'm talking about. We just got the revision. It's favorable. We just submit the revision. I'm sure we'll get it. As you can see here, this is without any pre-shaping the grasp. But now we are going to pre-shape it. It's quite smooth, quite natural. You see, the first finger touches, the second one comes nicely on that one. Maybe I'll be faster. I think this is the one multi-grasp one, like in natural hands. You do this, if you want, you can use the other fingers to do the other gestures. So this what we are trying to do in this video, you see now the finger is handling something else. So this is also thanks to the work we have been doing to identify where the fingers are and what else we can do. So maybe I'll stop here, and this is the image. I always like it. This is the world without engineers, and I know how the world will be without scientists and collaborators, multidisciplinary research. And more importantly, as this center demonstrated, we created synergy and demonstrated this advanced equation that this one is much bigger than the sums. So I thank you, and looking forward to getting your questions and continuing on this conversation. We got lots of initiatives happening, some patent applications, some talk with some industry. So thanks to ACES and its members. So I will stop here.
Thank you, Professor Gursel, Alici. So any question from audience?
Come on, I don't think it was that boring.
Okay.
There's one in the chat from Rob Cowan, Gillian.
Yes, okay. So we have one from Rob Colvin. Seem like there are great application possibility here. Is there any industry partner who are likely to want to be involved?
Yes, thank you. I think I mentioned one of them, this Tasca Prosthetics in New Zealand. They are interested in our work on identifying the user gesture using a patent application. Currently is in the process, rather than using surface electromyography electrodes, which is in the current hand. And we have our own human-machine interface, which is more stable, more durable. And so this is one piece of work. Also, another company called IP Group, they are interested in, again, our work on sensory feedback and its applications to various areas, like cooperative robots or cobots. We are doing a piece of work for them. And also on gripping, recently we partnered with CSIRO in Brisbane, how we can control the finger force to handle some agricultural produce. So we got a funding project with CSIRO Data 61 and just started an advertising research fellow position based on our work using machine learning to control the touch and to differentiate between soft and hard objects and agricultural produce. So lots of opportunities already, some of them are happening.
Thank you. So we got another question for you. This is from Wahid. Thank you, Gursel, for the great achievement. How close is the soft robotic product to the market? Thank you.
The market, thank you, Wahid, and nice to hear from you. I remember many years ago, you were a PhD student on artificial muscles when we were working. A brilliant question. Some soft gripping companies already are on the market. It's called Soft Robotics. It is a spin-off company from George Whitesides from Harvard. These were some initial initiatives. And so there are lots of challenges. It's still, this area is growing, especially there is a need for smart materials where we can control the stiffness, where we can have some robotic concepts like our flashes, like having sensing, actuation, power source, energy source in the same body. So especially in the area of handling underwater surveillance, manipulation, agricultural area, there are some spin-off companies. This human-machine interface, the work Facebook is doing about haptics, touch sensing, also requires safe interaction between any device and human. So you need to have this touch sensing, which is based on principles of soft robotics. So there are lots of opportunities. It's not a totally new area, but thanks to smart materials as well as additive manufacturing, now we can tailor these enabling technologies to develop application-specific robotic solutions.
Okay, thank you. So I would like to introduce our next speaker, Professor Brett Paull from University of Tasmania. His talk is Light Camera Action, the development of fiber-based electrofluidics. Professor Brett Paull, please.
For those of you who haven't a clue why it's called Lights Camera Action, I worked at, because most of the stuff we've done on fiber-based electrofluidics is done in a dark room with a fluorescent camera. I worked out with a number of people doing research in this project over the years, a number of years and weeks and so on. It's about 8,500 hours in the dark. So that's why it's called Lights. Turn on the camera and see some action. What I'm not going to do is give a big overview of the entire electrofluidics theme, because we don't have time, and also some of the things, as Rob alluded to, went as far as they could go at the time, and sort of they didn't die a death, they just went on the back burner. And other things like the composites were based on people being here, the composite printing work, and they finished their PhDs a few years ago. But the fiber-based electrofluidics seems to have a lot of legs and carried on, and is still carrying on, so I'm focusing on that. Okay. Right, so I'm not really sure how we got into it, to be honest. We started with ACES 2 coming on board, and we were looking at characterization of some fibers. John Mark had just come on board and was looking at using contactless methods of characterizing fibers. That was quite successful and seemed to work, and it led to later papers. Andres there did some work later on, and it's carried on doing contactless analysis of fibers. But somewhere in that mix, in the early days, we started looking at electrofluidics on fibers and applying buffers and putting a voltage across there and seeing if we could move things along those fibers. Probably with the initial idea of using contactless conductivity as a detector, but it didn't go down that route. My talk is going to focus on the people and celebrating the people involved in all of these projects. We talk about impact, and often it's new labs and big grants and new devices and so on. But impact is also where these people end up going and what they end up doing. So I'm going to celebrate some of these that I've worked with and show you where they are. John Mark there is now in Barcelona as a principal investigator with a research center there. And still is in contact and still supporting one or two papers that we're putting through. So that's where we started off. And John Mark at the beginning realized that we could do some interesting things on fibers if we put, as I said, put a buffer across there, apply voltage. We could move things around and concentrate them. We could use different materials, and we could use the expertise in-house and in Wollongong in 3D printing to make platforms to do this sort of work, to optimize those and to iterate those very quickly. So all of this work moved forward very quickly because of the revolution that 3D printing is and was, enabling us and the students to do interesting things almost immediately and change and as I said, reiterate those devices. So we're claiming we've established a new field of fibre-based electrofluidics. I don't know if we did. I can't find too much being done on fibres before us. So we're going to claim it, and if anyone wants to disagree, they can. But basically, we realized we could do some interesting things. In the early days, John Mark was studying how to concentrate, how to couple different materials together, how to trap certain things. And we moved all the way through small molecules to large molecules, biomolecules, even to cells. So he did some work looking at bacteria cells and even applied that as a diagnostic to things like urine analysis for bacterial infection. So we rapidly moved through developing this as an idea into some simple diagnostics. And over that early period, 2016, 17, we churned through quite a bit of work and a few publications showing that this approach is very simple, but also very sample matrix tolerant. So you could use real biological samples, you could load real biological samples onto these types of fibers and do some interesting work. All of this was supported through Wollongong and the materials people there, and working with Peter from the start really on synthetic fibers and braids and mixing different materials. And it started to get some momentum. And during the middle of the ACES period, we were really doing some interesting stuff. So this is one of those examples. This is a paper which looks at direct metabolite analysis in complex samples. This, I think, is looking at urine and saliva and other sorts of samples. We moved forward quickly with the ability to make more elegant platforms to do this work on and tailor that to certain applications. As I said, we were working closely with Peter and his team, and I'm going to mention CMAC here because he was doing a lot of the material work and material development, braids and new materials and textiles. And then we started to move into different applications of this. So working with Zillian and Gordon and the team and Luciana, we started looking at whether we could do things like move bands of solutes through three-dimensional structures like gel structures, and that seemed to be quite exciting and seemed to work. And there's an image there where you can see that material traveling through a three-dimensional gel structure. And that triggered a lot of ideas about cell cultures, and those ideas are still there, and we're still talking about them and still exploring where that might go. We also, through CMAC and Peter, started introducing other things into these fibers like electrochemistry, electrodes to do on-fiber conversion or detection, so that we had a system where we could move, concentrate, target, isolate solutes, and also detect them or transform them or derivatize them and so on. So that's the way it was going. And during that period of time, with CMAC and John Mark and a few PhD students, there was quite a lot of exciting things happening. What we did realize was when you do fiber fluidics, we don't want to be in dark rooms all the time. Students don't like being shut in the dark room all the time. So some of the interesting things we could do were limited by how we could detect them. And so sometime in 2017, I think we got together and started discussing mass spectrometry, and we were luckily funded by a DP grant in 2018, and Peter, myself, and Wolfgang Buchberger, who's an ambient mass spectrometry expert who was on the grant initially, put in a DP which was funded to use ambient mass spec. And as you can see, we can do interesting things like use separate proteins and isolate proteins on fibers, but we can't detect them without more powerful detection options. And so ambient mass spectrometry was one of those we thought about. Turned out quite successful in the end. So we had a wonderful student in Liang Cheng, who's now at the University of Illinois in Chicago, just he finished about 6-7 months ago. He was doing this work, and in the middle there you can see one of the images which got one of his papers which got on the front of the Analchem, which shows the isolation and focusing of a protein band on, or actually an alkaloid, I think, on a fibre, a fluorescently tagged alkaloid, or actually it's fluorescent naturally anyway, and its detection using mass spec and a very clean detection signal, because this fibre-based electrofluidics process allows you to put on very dirty, complex samples, but it keeps a lot of that matrix isolated while you focus your targets. And so we got beautifully clean mass spectra for alkaloids in urine samples with ambient mass spec as a detection mode. So that proved very successful, and we're still aiming to do more things with that, because it is, as I said, a beautiful technique for cleanup of biological samples prior to mass spectrometry. In Wollongong with Peter, Joaria was doing similarly complex things on fibers, again, introducing some electrochemistry, but also looking at braided structures and improving the control of electroosmotic flow through better structures, better materials, and inclusion of things like the bipolar electrode setup shown there. Again, very elegant sort of work, enabled us to control quite precisely where things moved on fibers and separations of certain targets and so on. Where we've moved to now in all of this is to do perhaps more complicated things and to use these sort of platforms in moving closer to sort of pre-commercial platforms, if you like. And one of the things that came out of COVID was everybody's interested in swab analysis. We also have other projects. Swab analysis seemed to be important in pharmaceutical and in industrial applications. And so we wondered if we could couple a swab directly with a fibre and do extraction from a swab onto that fibre in concentration. This is Arushi in the slide, who came on board to develop this, working with Paull and myself. It led to a provisional patent last year where we can quantitatively extract and remove solutes from a swab, all sorts of different applications, and transfer them onto a fibre where they're concentrated and trapped. And we can also include in that system modified trapping zones, and you're looking at a graphene coated fibre which is knotted around a nylon fibre, and you can see how it quantitatively traps that fluorescent, probably just fluorescein there, upon that trapping zone. So now we've been given a little bit of money by the University of Tasmania to develop that into a viable commercial platform for demonstration, where we can take some swabs and isolate a particular target. In 2021, we had Liang with us, and Liang worked with Peter at Wollongong and Gordon within the electrofluidics and diagnostics cluster, but more focusing on printing of porous materials and electroosmotic pumps. While he was with us, we transferred him onto a fibre project where, again, we used a modified fibre. In this case, we used a liquid crystal graphene oxide trap. He used his 3D printing skills to print a little cell for us to reproducibly modify that fibre with a trapping zone. And then we were looking at trapping and hybridization of DNA, or single-stranded DNA, upon that graphene oxide trap. And the figure that Liang put together on the right shows how that worked. We have fluorescently labeled single-stranded DNA. It migrates under applied potential there onto the trapping zone. It's completely trapped. The fluorescence is quenched. And then we can flow across the top of that its complementary strand of single-stranded DNA. The two of them form or hybridize, and we get the double-stranded DNA, which actually comes off the graphene oxide. And the final slide image at the bottom on the right shows that double-stranded DNA coming off the graphene oxide. So we're doing trapping of single-stranded, we're flowing across its complementary DNA, we're doing hybridization on the trap, and then migrating off. And there's lots and lots of applications of this that we're now interested in exploring. But I said it's about people and celebrating people, and I just want to give this very brief story about impact. This is the Acromonitrix story. This is not a technology of ours. It's a technology of Tell Labs in Ireland, but it started off with a conference in Ireland in 2016, at which this gentleman, I don't know if you can see my marker, but this is Owen Murray, came up to me, and Dermot Diamond had sent him to me to talk to me because he'd started a PhD and was struggling with microfluidics detection, chromatography, and so on. So Dermot had said, you know, the ACES team, the Across team down at UTAS can help you out, go there and work with them. So he had a bit of a problem student. He offloaded it to us. Thanks very much, Dermot, but it worked out fantastically well. So Owen came down to work with us. We agreed to host him here. He actually came twice. One time broke his leg, still carried on working in the lab. As you can see, he started off working with some familiar faces, including John Mark. But he was introduced to VPOL and what VPOL could do, and we've started printing some 3D flow cells with some 3D detectors cells and so on, and started doing some very simple portable instruments that he was interested in. With the initial ambition was for them to build a portable IC-based analyzer. That was what we understood. So things started working. We could do certain things down here which helped him along. And that generated a lot of publications while he was here. He was very productive, a number of publications, one after the other. And as you can see, by the time he got back, within a year or so, the company had produced the first prototype instrument. So this is the timeline to all of that. It still continues. We're still working. There was some other work he did here with 3D printed microfluidics, but Owen is still putting out papers now. There's one came out last year. There's another one just come out this year on upgrades, continuous upgrades to that technology. And he's got a couple of covers of journals from his work. But the human story to all this is, well, actually, before we get to that, that led to a linkage grant, which was funded last year, which is fantastic. Tell Labs are in with us, where we'll help to improve that technology and develop it. And in terms of people, we've taken on a new student in Yong Ling, who's now on this project, and Kurt de Bruyne is starting his industrial placement with TE Labs in May. So this goes on based on 3D printed components within that system. VPOL's there, he's part of the grant, but actually in terms of his 3D made spin-out company, which was mentioned earlier, we did supply Tell Labs with our first big order from that entity, although they didn't end up using them. So the person story here is that Owen, who had a very weak start, went on to win the gold medal in the European Young Scientists Award, which was fantastic, and now is R&D manager for Tell Labs in Ireland. So from humble beginnings, working with the guys here, and that mix of analytical and material science that ACES is here just worked wonderfully well, and that's a great story. Where are we going forward? We've just got a DP funded with Jeremy and Eva and myself and Australia to take some of that 3D printed cell culture work forward. The stuff that Rob alluded to earlier, which sort of stalled, but we're going to reinvigorate that and get that going again. I just want to say that VPOL is not on that grant purely because he's full up with his DECRA and other DP. He couldn't be named, but VPOL was very much instrumental in helping us put all this together. So big hands up to VPOL, who couldn't be on it because he was just full, too successful. We also had great reviews come back for our proposed training centre. I'm very optimistic, although with ARC, you can never be too optimistic, but that did get a good reception. And I think that is, although it's very much separation analytical science based, founded on a lot of the great working networks and just great people that we've met and got on with over the years, which ACES has helped immensely with. Yeah, we've got 70 odd publications from the theme, but the big number there is 60% of them are multi-institutional, which is fantastic. We've learned to collaborate and do a lot of things that we couldn't do on our own, and that's been great. And that's probably why they're cited so well. I think they're close, getting up there to 2,000 citations, which, given we're a small group in the Centre of Excellence, and we are sort of feeling the benefit of that now in terms of citations. I think everyone should be pleased with themselves for that. So it's been very emotional. I've learned an awful lot for myself. The impact on me has been great. We've had a lot of fun in this theme, I think, and everyone has been great. And we've had some wonderful theme meetings, and everyone's had a good laugh, which is fantastic. And most of the people there are doing wonderful things, either still within the university system or with the industry or research elsewhere. So thanks very much. That's all from me.
Thank you. Any question from audience? I got one from Gordon. So he asking about multi-component analysis on thread. Can you elaborate more on that?
Did he write it down, or is he just, I can't see his question anyway, but well, multi-component analysis. So depending on how long your thread is and how much time you've got, you can separate quite a bit of stuff on a simple thread. But I think the killer advantage of this is its ability to handle quite complex samples. We could put blood on the thread, and we've already done that, and Arushi's done that, where we can actually put blood which hasn't been treated or pre-treated in any way. We can separate out the red blood cells from metabolites within the plasma, and that's a real advantage. So that when you're talking about potential diagnostic platforms, you need substrates which can handle complex matrices, and some of these simple threads and braids, and we can also put traps anywhere along those, and we're looking at different materials where we can covalently attach trapping zones or cleanup zones. Very, very flexible. Once you get the robustness and the reproducibility down, you've got a substrate which is very simple, cheap, but can handle some quite complex samples. So of course, you're never going to get hundreds of different compounds separated on a thread, but quite often in diagnostics, you're looking for one within a complex matrix, and that's the challenge, and that's very much doable.
Thank you. So I got a question from Wahid. Thank you, Brett, for all this outstanding research. Can we propose any practical approach for hollow conducting nanofiber in microfluidic area?
That's quite specific. Can we what? Can we
propose any practical approach for hollow conducting nanofiber in microfluidic area?
Not off the top of my head. Hollow conducting nanofiber. I mean, any conducting nanofibers are quite interesting to us, and we've used lots of conducting materials, nanomaterials as fillers in composites for 3D printing microfluidics, and that can be 3D printing within those microfluidics sort of trapping zones or detection zones, or other ways of derivatizing, changing, or manipulating solute you're interested in. So that's a possibility, and of course lots of people are looking at ways of producing nanofluidics which have, or microfluidics which have, various zones and functionality within some of the channels and elements within the system. So, but no, hollow conducting nanofibers off the top of my head. I'm sure there's lots of different potential uses. You can send us some, we'll play with them.
Any more questions? Okay, for the interest of time, we move on to the final speaker of this session. If audience has any more questions, you're welcome to use the chat box and just key in your questions. So our final speaker in this session is Professor Linda Hancock from Deakin University. She's going to talk about interdisciplinarity, a political science lens on electromaterial energy science. Thank you.
Hi, thank you very much for the introduction and also the opportunity to speak. Well, as you all know, within the Centre for Excellence, there are two main foci, the biotech side and the energy side. In epi-energy, of course, that's been more of our focus, and conducting interdisciplinary research has been a challenge and a great delight, I'll say, over this 5 to 6 year period, because of the interactivity that we've had with the scientific side, trying to then look at the key public interest, ethical issues, climate change, justice, circularity and energy systems, which has been our focus. Oh dear, I don't think I can change. Oh yes, I can. So the key issues that we've been engaging in and questions I've outlined there. I suppose a few observations. Technologies change over time and this needs new models of evaluation. Ethical procurement needs to be looked at all stages. What are the impacts of information systems? What are the quality of systems and devices over time? What are the long-term environmental effects? What are the global renewable issues? What are the ethical issues? What are just transitions? So a lot of these questions require, of course, too, new regulatory responses. So it's not just about policy, but it's also about regulation. So back in 2015, I got fascinated with looking at Tesla and the new cars were being discussed. Of course, a lot of them are a lot more expensive than what was mooted in the first instance. But what is it about the ethical materials for these new battery-driven and electric cars? And are there alternatives to lithium-ion batteries and certainly alternatives to cobalt? Because, you know, it should be a conflict mineral if it isn't. And the majority of cobalt comes from conflict-ridden zones in Africa. So what I'm going to do is just do a foray through some of the work we've done and then end up looking at frameworks, methods and tools of analysis. So I'm going to start with looking at the carry through from that first interest in batteries and the ethical components in the batteries. And so in the lab, which was a piece published with colleagues from ACES, including Michelle, we looked at ethical procurement and also critical materials that are critical to transitions. So it's important to be looking at these, obviously, and this over the last 6 year period, it's interesting to observe that a lot of what we flagged as quite new issues are now on the pages of the national papers, and we're looking at our own capacity in Australia to be in the latest questions, can we produce cars again, having had 4 years without that? And because we've got a lot of the natural endowments and the materials and the expertise and the systems, etc. So in this piece, we looked at the renewable energy regulatory environment and also the supply chain and product life frameworks. And so the actual method was that we looked through the cupboards in the battery labs, at Monash and Deakin, and we identified key suppliers by their packaging, and we looked through the purchase orders for 1 year, and we identified the companies that the ACES project labs obtain materials from, and we then subjected those companies to tests for transparency, accountability, human rights, environmental and ethical probity and cleaner production. And we then looked at the regulatory environments, looking at international frameworks, OECD, due diligence. Dodd-Frank Act is important in the US and also in the EU, which has been a leader. So we were looking at how the work in ACES, like ripples in a pool, how it can engage with these broader debates, and how from the lab point of view, we can be making sure that young researchers choose materials with an ethical lens, and also with regard to future regulatory issues that may facilitate or impede the production of devices or products. So that research set the framework there. In terms of the research on Bolivia, that was prompted by taking a country in South America where the president wanted to promote his country, a poor country, but located very importantly in the South, in that continent. And Morales wanted, through public-private partnerships or PPPs, to create partnerships with commercial operations in order to go forward and develop the industry and promote. Now, that hasn't necessarily happened, but it was interesting and germane to look at how the PPPs might link with the UN Sustainable Development Goals, and also to put forward how we might evaluate this and what the principles for an evaluative framework of these sorts of PPPs might be. And so what are the barriers and facilitators using PPPs to a more integrated renewable energy battery supply chain? And those questions are just as relevant to Australia as Bolivia. But you know, it was germane to take Bolivia in that case because it's a very pivotal South American country in terms of the natural resources of lithium in Chile, Argentina, and Bolivia. I'll move on now to the next research, which was 3 pieces around looking at energy security. And so in this case, I'll talk first about the solar electricity exports to Indonesia in terms of the ASEAN grid, and then go on to Japan and exports to Europe. I suppose the main point in engaging with this is how do we define and operationalise energy security? And also in terms of renewable energy exports, the old economy is about pipelines and tankers, and how can these be repurposed for a new economy that's powered by solar, wind, hydro, and electric cables and other means of sharing electricity. So in terms of the exports to the Asian region, obviously that's the Australian market. And, you know, within the context nationally now of saying, well, you know, we need new technologies, and the COP21 meeting last November was very instrumental around leaving coal in the ground and also raising questions about gas as transitional. And so again, we come back to Australia having great potential for exports to the Asian regions as more of a superpower within the region. And so a lot of these, what was signalled 20 years ago is happening now. Older, cheaper forms of energy are retiring. On a daily basis, we hear of coal generators retiring earlier than what their extended frameworks had been. And at the same time, we in Australia have one of the highest per capita emissions. So it's not like we're just wanting to be good guys exporting. We need to work on ourselves as well. And in terms of our own government, a lot of the work we've done in the papers we've written has a policy context section dealing with the government subsidies to the fossil fuel industry. So the context we've been working in is one where it's quite difficult without government kickstarting subsidies and tariffs and other sorts of facilitative policy triggers. It's been quite difficult, and that impacts, of course, on the research environment that a lot of our researchers within ACES are working. And the Minerals Council of Australia has been a very strong lobby. And you might recall that Santos even had a desk at the Australian Pavilion, which people were appalled at, that at a COP26, a major emitting company had that kind of persuasive power, I guess, on the government to be the. These are our natural endowments in terms of being, you know, one of 5 zones of very high solar energy in the world and globally. And so obviously what's been happening more recently is large utility scale installations using solar going to these areas of high solar intensity, and also being geared of the Pilbara in particular, for example, to export. So the paper around exporting electricity to Indonesia looked at the geopolitical issues, like what are the issues when we start doing these new forms of cross-border renewable exports? Because a lot of the energy security work has been very nationally focused around supply and demand, because that suits governments and it suits the economists. But it's a neo-lib kind of conservative framework that doesn't necessarily lend itself to optimising outcomes for global climate change. And then there are the tensions in the South China Sea to take into account with any sort of cross-border and export contexts. What we did in that study was look in particular at a pilot study in the Pilbara, a feasibility study, and looking at their aim to export to Indonesia for the ASEAN grid. This diagram shows the ASEAN grid, which is a form of moving electricity around ASEAN countries and using the same subsea cable technology as Tasmania. So this is a major export potential for Australia, but we were raising questions too around what were the security and geopolitical implications and how would we analyse that. So when you're in the social sciences, Christina once asked me a really good question. She said, how did you get that framework? And so the frameworks, we don't just pick one, we do some analysis. In this case, we looked at 50 articles on energy security frameworks over a relevant period in refereed journals and also in organisations such as the World Bank, and there are some of the journals we chose. And there's, of course, no definition on, no clarity and consensus on a definition, because it's a multidimensional and dynamic kind of concept. But we need to have a definition that includes geopolitical, economic, environmental, human security, and ethical issues. We get to the ethical a little bit later. But as I said, these frameworks have been dominated by economics, followed by technical, and these other more social but very important issues have tended to be more peripheral. So in terms of that article, we settled on a framework and then we applied it to the cable project. And we spelt out some of the implications around cross-border electricity grids and the problems with regional geopolitics and the challenges that this poses, and also some of the new more technical innovations around ammonia and perhaps ways of supporting the export of hydrogen as ammonium rather than hydrogen in purpose-built carriers. But in that case, it was looking at solar fuel being very advantageous in terms of proximity from the Pilbara to Indonesia and export to the ASEAN grid. And so the third piece we wrote was around, the second was around exporting brown lignite generated hydrogen to Japan, because this is sort of a legacy project for the Victorian government. I think the minister's quite embarrassed about it, really, because as time goes on, nobody wants brown hydrogen because it has very high emission pedigree. And also this project was predicated upon carbon capture and storage into Bass Strait. And now we've had so many people confirming that CCS is not a verified method, even if it might have worked in some contexts. It's been usually small scale and below expectation and will take too long and cost too much. So it doesn't meet the criteria of just going solar, because a lot of this is driven by providers wanting to use coal and say somehow or other it's clean. And so in that piece, we focused on just transitions and asking the ethical questions. This fits in just with the piece previously around our dependency and Japan's dependency on us but also our potential in terms of using renewable-based energy to export to the countries most based around a hydrogen economy at the moment, which are Japan and South Korea in our region. And so this is a map, sort of a stylized diagram of the Gippsland project, but it has emissions at the site, but also is predicated upon CCS, which I might add wasn't part of the pilot and has not been implemented yet. So the security for whom, for which values, for what interests and what threats, they're very useful questions to ask in the context of comparing the different sorts of hydrogen. And so in a piece that Renew Economy did last year, they called it Japan's pivot to renewables will kick Australian exports right in the thermals. So again, there's pressure from within Japan to be green. And so you wonder about the risk of stranded assets with this sort. Just while we're talking about just energy transitions, Linda Wallachine has been doing some work on this in her PhD and looking at socio-technical renewable transitions and the concept of energy justice and just transitions. And in terms of policy, you've got the alternative of either following business as usual, which is path dependency, and it results in inertia based on prior choices and a sort of lock-in energy technology, which probably epitomises where we've been in Australia under this kind of climate policy wars scenario where coal and gas and the fossil fuel industry have been dominant, as compared with path creation, which focuses on the agency of change and change makers and entrepreneurs to define new transitions. So the third piece we wrote and researched in terms of energy security has been looking at the impact of EU carbon border adjustment mechanism on Australia as an export nation of hydrogen and Germany as a net importer. And it has two interweaving themes of the potential impact of this carbon border adjustment mechanisms on our exports to Europe, and also addressing a gap in research because there's little written, it's a very new area, on the opportunities and risks of such a huge entity as the EU with 27 member states implementing what amounts to a tariff border tax, but isn't a tax, and that's also fitting within EU rules, WHO rules and the fair trading rules, because it's able to create a level playing field, because European enterprises generating energy are subject to climate change rules and a carbon tax. So therefore they say they need to be on an equal footing with those trying to export into Europe, and that's quite acceptable, and that seems to be the case. So what we did was look at import-export case studies, looking at Australian brown, blue and green hydrogen exports to the EU, and looking at German imports of blue and green. And both were based on company case studies, based around looking at various company documents, annual reports, and so on, coming up with a risk and opportunity analysis where on the left-hand side of this table, you see our energy security dimensions. We added a 7 to this framework. So there's just an ethical, socio-technical from the previous paper. And then there's supranational carbon mechanism impacts on imports, exports to cover what's now called carbon diplomacy. So in terms of the Australian analysis, looked at Latrobe Valley brown hydrogen, Santos Cooper Basin blue hydrogen, and green hydrogen from 2 operations, one with Japanese partners and one Origin Energy and Japanese partners. So the Japanese are hedging their bets, obviously, and investing in renewables. And possibly it may be that the Gippsland project becomes something of a relic of the past as we move forward. In terms of the German analysis, risk and opportunity was based on 2 companies, 2 imports, because Germany is a net importer of energy. Although in the longer term, Germany's renewable energy seem to reside in its potential for offshore in its coastal region. But for now, it's needing to import. And so we looked at the various risks and opportunities in those terms. I'll get on to the 4th area, which is around power and interests analysis, because what drives so much of this is who makes policy and whose interests, what are the values underpinning it, and how does it all work? And so in terms of the power and interests analysis, I've done some work on this in relation to dangerous consumptions, and we've been applying the taxonomy to big carbon energy because it's the global harms, it's the commons of the air we breathe that's polluted by CO2. And people working in the corporate political activity analysis area acknowledge and want these frameworks to be used more broadly. And I've been working with folk from University of Bath, and we've just submitted to PLOS Med a cooperative article called Political Activity Model, a conceptual model and taxonomies of unhealthy commodity industry influence on public policy. And so we've come up in the research, coming back to the research that I've done, the 9 key strategies used by big energy to influence government for business as usual, 9 framing strategies and 26 tactics. And I've said in the slide, we'll see these every day until the federal election, because these are the sort of sliding things that governments do to through lobbying, through shaping the evidence base, through constructing a narrative of unintended negative consequences to the economy. Like if we do this, there'll be a loss of jobs. We're hearing that constantly with coal. Constituency building, fragmentation and destabilisation, and saying they're all working responsibly. So that research has been quite central to analysing the power and interests. So then to get on to just reminding people of Matthew Cherian's research in India around energy and disasters, and a piece that we published. And his research is looking at improved design and development of disaster resilient energy systems and seeking to inform disaster policymakers. I will add that Matthew has become, he was CEO of Help Age India, the biggest charity in India, and he's now, over COVID, been chair of Care India. So Linda Wallach's research, enabling low carbon community energy, has also been important, and looking at the need to invest in localised energy production. Again, the role for government in facilitating community energy alongside the different scales of energy that we have is very important, and her comparative research is going to be very important in that respect. So some of what we've done, just finishing up, is in the last 5 minutes, is ethical supply chains in renewables. And we have had some impact. A concrete illustration of the ACES energy influencing the University of Renewable Investment has been at Deakin, where a battery was chosen for the microgrid, and thanks to Maria too, that does not contain cobalt and that yet meets storage efficiency and cost criteria over the long term. And it's the first Australian utility scale microgrid battery to not have cobalt. So in terms of international collaborations, we're a small bunch, 4 of us, but we've had, and now probably 3 for the last 2 years, we've had a number of very important collaborators in some of this written work. And I want to just say in finishing a bit about the social science toolbox, because people say, well, what do you do? Because it's so different to science. And we develop frameworks, and we do this in a systematic way around circular economy, just transitions, energy justice, and so on. Then we have methods and tools of analysis that have a lot in the social science literature that we draw on: discourse analysis, framing, narrative, stakeholder analysis, systematic reviews. And evaluation is very important and pivotal. And I might say it's important in a lot of the technical work done within ACES, and was going to be part of the centre that Maria put forward. So concluding, I want to say that natural sciences have shorter papers with bigger teams than we do. And we've noticed lab scientists often repeat experiments a lot through fear of being disproven. A lot of the impact within ACES is understandably around patents, devices, and technology. Therefore, how do we demonstrate impact? And so we contribute to debates. We have key publications. We also have to distill these for absorption and citation. We do media appearances. We conduct our research to inform policy development. We promote research to policy developers, and we play a role in systematic evaluation. So it's harder to pinpoint. We don't earn universities money necessarily through the design and patenting of widgets and devices, but we nonetheless try to demonstrate our impact through those things. So thanks for bearing with me, because I did plan it for 20 minutes and we're just right on 23. And I want to thank ACES and also the ethics area, and Sue and Gordon, Maria and Doug and David, who I've worked with in particular, and Tony and Tracy. So thanks.
Thank you very much.